Welcome everyone. So my name is Felix Emeka Anyam. So I'm happy that you could join me today for this insightful webinar. So it's how will I put it now? It's a webinar that will have a little bit of twist because the whole essence for this webinar is to give you a strong idea or a good insight on statistical significance levels. So I would like you to progress with me. I would be in the PowerPoint slide. I would go to the blog I asked you to read. I would go to the website. I would go to a journal I've published. I will open statistical software to show you. So I'm going to be moving around a little bit because the whole idea of this webinar is not just to provide theory and theory and theory, but just to also show some practical demonstration on how these things, are done. And I'll try as much as possible to use examples as well, that could also help the communication of this sermon. So we would begin right away. So the first thing is the title of this webinar, which is Statistical Significance Level, the Science Behind the Earth in Research Publication. My name is Felix Emeka, and these are my details. So what is research? I wanted to start from here because this will really help, okay? Now, the definition I liked so much is the part that says it's a systematic investigation. And when we say a systematic investigation, we're talking about something that has a pattern, something that has a process, all right? Something that is reproducible. So if you do it, some other person somewhere can reproduce it. That's what research is all about. So if you're doing something and it's not reproducible, your methodology is not reproducible, then it's not a research. Maybe it's something else. Let me give an example. You want to interview some women of reproductive age. Sorry, I would be using most examples from my background, which is epidemiology, public health, biostatistics, and most recently data science. Please pardon me, but when you're asking your questions at the end of the webinar, you can use, your own field of study. I think I would be able to grasp. Research is universal, so it doesn't really matter the field. The principles are the same. All right. So back to the systematic investigation. Just imagine you want to interview women of reproductive age. You want to ask them some things about their habits so that you will be able to know if they are at risk of preeclampsia. Preeclampsia, it's a condition that affects pregnant women. So it's called hypertension in pregnancy. So you want to interview these women, that are coming to the hospital, probably for antenatal care visit, mostly those that are pregnant. And as the researcher, you don't just say, oh, I'm going to interview 100 women. Oh, I'm going to interview 200 women. That's the much I can take. No, it's not allowed. It's not done that way. You have to follow a systematic process, meaning that you have to calculate what they call a sample size, and you have to use a sample size determination method. And depending on the study design that you're using for that research, that will inform what sample size formula that you're going to use. You don't just decide the number you want to take. Another example is you don't just decide how you want to select the participants. So most hospital-based studies, especially those that you're recruiting participants from the hospital, we usually recommend the systematic sampling because you may not be able to have like a sampling frame meaning having all the participants you want to interview in one place. You have a list, then you now use simple random sampling to pick the number you need based on the sample size you've calculated. That may not be possible in a hospital base because as these women come, or as these patients come to the clinic, they get their treatment, they leave. So they may not be able to wait for you. So we often recommend the systematic sampling where you calculate a sampling interval and you're able to say, okay, every Every fifth woman that comes, every second woman that comes, you will interview and recruit into your study based, on the sampling interval you have calculated. So you see, these things are processes, more like a standard operating procedure. So we have to appreciate the fact that as long as we have said we want to do research, we have to follow those systematic processes so that anyone anywhere in the world can see what we have done, be able to reproduce it, or be able to replicate it in our setting. So the other thing I also want us to appreciate is the scientific method itself, where it all starts and where it ends. Now, research, like I mentioned, always starts with a problem. There's something you want to solve. That's really the motivation for doing research for majority of the people. You have identified a problem and you want to be able to solve that problem, you know? So you state your problem, what that problem is, and what you want to solve. So after you've stated that problem, it could be like the example I gave. You want to be able to measure the prevalence of women that are having hypertension in pregnancy. All right. So you want to be able to calculate if the number of the women that are pregnant in that facility, how many of them have tested positive for preeclampsia. Okay. So that may be what is informing the problem, the number of preeclampsia or the prevalence of preeclampsia. So that is motivating you. Then you're able to formulate a hypothesis, all right, which I will provide more information as we progress. Then you're able to design the experiment based on the study design you want to use, whether it's a cross-sectional, it's a case control, it's a cohort, depending on your field. Then you design the data collection to either physical data or virtual online data. You collect the data, you analyze the data, more like providing a summary that will make it easy for people to understand what you have done, and you draw up your conclusion. So that's how the scientific method works. So we would progress with the next slide, which is the anatomy of a p-value. I would now switch to the blog itself. But before I do so, I want to confirm if you can hear me clearly. You can drop it on the chat if you can hear me very clearly. Yes, okay. Very good. Thank you so much. So let's progress to the blog itself. So I hope you can see the blog. I hope you can see the blog. Yes, okay, fantastic. Now, this blog is similar with what we are talking about, which is the statistical significance level, the science behind the earth in research publication. Sorry, someone is writing on the screen. Okay, thank you. So the first thing I would like to say is that imagine you are in a court of law, all right, in a courtroom. I read a lot of John Grisham novel, and I know most of us did because I've always loved the legal system, anything that has to do with the courtroom. And why I'd always loved the legal system, because of that word, evidence, where decisions are made based on evidence, not based on sentiment, not based on what the judge feels like or what other people feel like. So imagine a courtroom where someone has been accused of committing a crime. Now, in that courtroom, you would have the jury, and the jury, their role is to listen, to the parties that are involved. You have the prosecutor, whose job is to report the evidence and to ensure that if the crime was committed, the person that commits the crime should face whatever penalty it is. All right. Then you have the judge itself that will look at all the evidence and be able to make a decision. All right. You have to appreciate the fact that what the jury decides and what the judge decides are based on one word, which is evidence. And according to the Oxford Dictionary, evidence is the available body of facts or information indicating whether a belief or proposition is true or valid. These two words, true or valid. All right. So this is simply where the whole idea and the whole essence of statistical significance was informed from. And they use that word p-value, which is the probability value. And I have a paper that I also put at the end of the journal of this blog, which you can actually see as a reference to show you that this word, which is the statistical significance, had been there since the 1700 and has been demonstrated in what they call the null hypothesis, which is the first instance where it is used, where they wanted to check if a difference exists between the number of male and female births. So you will not be able to appreciate statistical significance level and remember evidence if you do not appreciate hypothesis. All right. Now, what is hypothesis? Like I mentioned, you want to do a research. You identify a problem. Now, that problem you have identified will inspire a hypothesis. Now, in this case now, we're going to be using COVID-19. All right. And the problem you've seen is probably the prevalence of contracting COVID-19. That is the problem you have identified. So you want to see how you can solve that problem of people contracting COVID-19. Now, in solving that problem, you have to formulate a hypothesis, meaning that you have to brainstorm on things that you think would be promoting that problem or limiting the incidence or the prevalence or the promotion of that problem. So for example, you now said knowledge, poor knowledge. So what if people have poor knowledge of COVID-19? Will that increase or would that lead to a high contracting rate of the virus? That's a hypothesis you are now thinking. So a hypothesis is more like you have identified a problem. You want to be able to see what are other parameters that will either enhance, promote that problem, or minimize that problem. So you're thinking about knowledge now as an example. If they have better knowledge, will it reduce the prevalence of COVID-19? If they have poor knowledge, will it increase the prevalence of COVID-19? So for you to be able to state a hypothesis, you have to have two variables. One variable is called the independent or explanatory variable, while the other variable is called the dependent or the outcome variable. And the outcome variable or the dependent variable is usually the problem that is motivating you to carry out the study. So you can have more than one independent or explanatory variables, but you can only have one dependent or outcome variable. So in this our example, the outcome variable or the dependent variable is COVID-19. And why is COVID-19 the dependent or the outcome variable? One, because it is the problem we're interested in, and two, because it does not stand on its own. Its rise or its fall is dependent on the independent or explanatory variable. That's why it's called the dependent variable. So for COVID-19 to increase in terms of prevalence or COVID-19 to reduce in terms of prevalence, it has to be dependent on some parameters. And one of the parameters we have identified here is knowledge, whether poor knowledge or good knowledge. So other things, can be the environment, where the person is found, where the person is clustered. That's also an independent variable. So the moment you have your independent variable and you have your outcome or the dependent variable, then you can create a hypothesis. And that hypothesis is usually two forms. You have the null hypothesis, you have the alternate hypothesis. So the null hypothesis is usually a state of no difference. That's the standard. So you state the null hypothesis. Now that we have our independent variable, which is poor knowledge, our null hypothesis can be there is no significant difference, all right, between poor knowledge of COVID-19 protective behaviors and prevalence of contracting the COVID-19. That is our null hypothesis. There's no difference, meaning whether they have poor knowledge, it doesn't make a difference in the prevalence of contracting the virus. That's the null hypothesis. Then the alternate hypothesis is the other way around. There is a significant difference, all right, or there's a significant relationship between poor knowledge of COVID-19 protective behaviors and the prevalence of contracting the COVID-19 virus. However, when you begin your research, like I mentioned in the first slide, you formulate the null hypothesis. That's the first thing you do because you have not carried out the research. You have only identified the problem. From identifying the problem, you have formulated a null hypothesis first. And that null hypothesis says there's no difference. So you go ahead to design your study, you collect your data, then you analyze the data. From the findings of that analysis, of that result, you will now make a decision whether you're going to accept the null hypothesis or you're going to reject the null hypothesis. So the null hypothesis, there's a state of no difference. The alternate hypothesis says a relationship in terms of difference exists. So meaning that someone with a poor knowledge of COVID-19, it could influence the prevalence or spread of COVID-19. So that's how the hypothesis works. So without the hypothesis, there will be no need for associations, meaning there is no need for testing for relationship between two variables. And there will be no need for test of significance or statistical significance. So it is because of that relationship, which is formed or informed by our hypothesis, that is what motivated us to actually begin to test for the evidence or test for the statistical significance. Now, look at the table 1, for example. This table 1 says knowledge of COVID-19 protective behaviors associated with the prevalence of COVID-19. So here we have our independent variable, which is the knowledge of COVID-19 protective behavior. We have good, we have poor. Up here, we have our outcome variable, which is the dependent variable, which is the COVID-19 test result, positive or negative. So in this case here, which is the COVID-19, the good or the poor, we want to be able to determine whether those that have better knowledge or those that have poorer knowledge, which of them will have more prevalence or more positive cases of COVID-19. So as we can see here now, poor knowledge, the prevalence here is 19.67. Why for good knowledge, it is 6.59. Our interest based on our hypothesis is what? Prevalence of contracting COVID-19. So our interest is actually in the positive cases. That is why in formulating this table, we have the positive cases first, then we have the negative cases following after that. So if you look at the prevalence, the percentage that has been calculated, this percentage is easy to do. How did we get 19.67? It's easy. We did 12 because if you look at the poor, it is 61. If you look at the good, it is 91. So to get the prevalence for the poor, we did 12 times 100% divide by the overall for poor, which is 61. That gave us 19.67. Then for that's for the poor positive. Then for the poor negative, we did 49 times 100% divided by the overall 61. That gave us 80.33. So that's how these percentages are calculated. So looking at the prevalence for poor, in positive cases, it is 19.67. And for good, it is 6.57. So looking at these, you can see that having poor knowledge of COVID-19 increased the prevalence of COVID-19. 19.67 against 6.59. All right. However, what is the evidence to show that 19.67 is truly significantly higher than 6.59? So that is why I was talking about evidence. Knowledge of COVID-19 protective behavior is like in a courtroom, and COVID-19 is like in a courtroom. All right. Both of them are defending their cases. At the end of the day, we observed that those that had poor knowledge had more positive cases for COVID-19 compared to those that have good knowledge. And what the jury will ask at the end of the day, fine, I am seeing that 19.67 is truly higher than 6.59. However, what is the evidence that 19.67 is truly significantly higher than 6.59? That's why the whole essence of the test of significance, which is the statistical significance, came about, which is the p-value itself. So this p-value is the evidence that 19.67 is truly significantly higher than 6.59. Remember that in your null hypothesis, you had said there is no significant difference between knowledge of COVID-19 protective behaviors and whether they would be positive for the COVID-19. All right. So you have now done the research. Your result has shown that the poor, they have a higher proportion than the good. So meaning that having good knowledge is better because it has a protection for you. What is the evidence? The p-value. And this p-value has a cutoff. Now, the p-value stuff has been there. All right. And it started with Ronald Fisher. I have the article. You can actually read about it. All right. I will share it when I'm sharing the recording. You can read about this article. A lot of things was said about the author in quoting Fisher. I don't know if you have heard of the Fisher's exact test. We will talk about it. But Ronald Fisher formulated the cutoff for the p-value evidence, which is 5%. That is 0.05. And why did they formulate that? They formulated that to say, in theory, a p-value less than or equal to 0.05 indicates strong evidence against the null hypothesis, as there is less than a 5% probability the null, which is the difference hypothesis, is correct. So in other words, we have formulated a null hypothesis, and that null hypothesis says there is no difference between knowledge of COVID-19 protective behaviors and COVID-19 test result, whether positive or negative. That's the null hypothesis we formulated. We have done the result, the analysis, and we've seen that the p-value, which is the cutoff of less than or equal to 0.05, that we generated from our association is less than 0.05. As you can see, we had 0.020. So what does that mean? This 0.020, which is less than 0.05, is 2%. So in other words, we can say there is evidence against the null hypothesis. In other words, there is less than 2% probability that the null hypothesis is true. So based on this evidence, there is less than 2%, or there is 2% and below evidence that we should accept the null hypothesis that says there's no significant difference, because the evidence here, which is the p 0.02, is showing that there is an evidence that poor knowledge could contribute to more COVID-19 positive cases. So our p-value is saying that there is less than 2% probability the null hypothesis is true. So in other words, we are going to be rejecting our null hypothesis. We're going to be accepting our alternate hypothesis that says that a significant difference exists between the knowledge and COVID-19. Yeah, someone put a yes. For the positive, yes, that is the calculation. Professor Ngozi, you've been raising your hand for some time, although we are reserving questions till the end in case this is, yeah, okay, it was an error. Okay, thank you very much. So let us proceed, and I'm hoping these aspects I have clarified. So I have another example here. All right. Now, if you look at the table 1, okay, so we will talk about the hypothesis errors now. And I know that you have heard about the hypothesis error, which is the type 1 and the type 2. All right. I need to mention this because now you have an idea, the hypothesis, but there's a type 1 error and there's a type 2 error. So in the type 1 error, imagine now you have done this study that I mentioned before, where you are associating the knowledge of COVID-19 protective behaviors and the prevalence of contracting COVID-19. You had gone to the field, you had collected your data, all right? You had analyzed that data. But when you ran your analysis did not show a p-value less or equal to 0.05. Your analysis showed a p-value that is probably higher than that. So a p-value, say like a p-value of 0.90 or a p-value of 0.80, something like that. So that is way above 0.05. So what that means is you're going to be accepting your null hypothesis. So meaning that a significant difference did not exist, all right, between the association you have done. But as the researcher, you didn't like that result. You wanted a significant difference to happen. Okay, so what did you do? You did what they call like a p-hacking. You adjusted your result, you tweaked a lot of things. And as a result of doing that, you reanalyzed the data and your p was now statistically significant. So initially, your p was not significant. So you would have accepted your null hypothesis, but you didn't want to accept your null hypothesis. You adjusted your data. And after adjusting your data, you got a significant value. So you have committed a type 1 error, which happens when you reject the null hypothesis, when the null hypothesis is indeed true. Your null hypothesis was true. There was no statistical significant difference, but you didn't want that. You feel, oh, nobody may publish this, or no publication house may like this result. Doesn't really matter. It's your result. That is what you found, but you didn't want to take the risk. So instead of publishing what you found, which is accepting your null hypothesis, you had to tweak your data a little bit, and so that you can get a statistical significant difference. So you committed a type 1 error. All right. So like I said, it happens when you reject the null hypothesis. When the null hypothesis is indeed true, but you rejected the null hypothesis because now you've adjusted the data to get a statistical significant difference. So if you have a statistical significant difference, of course, you are going to reject your null hypothesis. But this rejection was not a true rejection. You actually manipulated the data to actually inform this rejection. That's why it's a type 1 error. Okay, so we'll be looking at the type 2 error in the second block here. So when you're talking about the type 2 error, I would use an example of like a pharmaceutical company. Imagine like a pharmaceutical company gave you a contract to actually check if a drug they have manufactured significantly has side effects. So in other words, if we're to formulate a null hypothesis for that, it would be that there's no significant side effect of the medication on patients. There's no significant side effect of the medication on patient. That's the null hypothesis that informed you carrying out the research in the lab and all that. So after you have finished the research, you realize that there was actually a significant side effect of that drug on patients. All right. So if your research showed that there is a significant side effect of that medication on patient, what you would have done is to reject your null hypothesis. You informed the drug company and they were like, oh no, we would not like that result, because if you publish that result, people will not buy our medication because it will show that there's a significant side effect. So what we want to do is we'll give you some money and you would adjust the result and all that and bring the fact that there's no significant difference. So they're able to succeed, and they gave the researcher some money, and the researcher tweaked the data. And at the end of the day, the researcher came out with a new result that says, oh, there's no significant side effect of the medication on patients. So the researcher has actually committed a type 2 error. How? Because a type 2 error happens when the null hypothesis should be rejected. You had done the study, you saw that there was a significant side effect, so you should have just rejected the null hypothesis. But no, the null hypothesis should have been rejected, but the researcher failed to reject the null hypothesis because your hand probably has been greased. You tweaked the data and you're able to get another result that says, oh, the drug is safe. There's no significant side effect. So once the researcher, decide not to reject the null hypothesis, all right, he or she has committed a type 2 error. So understanding the type 1 and understanding the type 2 error is very, very key. All right. Now, you remember in the example I gave you previously, the judge or the jury must decide whether the accused is guilty beyond a reasonable doubt. Now, in terms of the researcher, the researcher must decide whether the data or the association you have done provides enough evidence to reject the null hypothesis, which is a state where nothing has happened. So your association providing enough evidence to reject the null, hypothesis is what is motivating you to do that research, because your null says there's no difference. So you want to be able to produce enough evidence to show that there's actually a difference. But there are situations where your research will show that there's actually no difference. You just accept it. Because if your research shows that there's no difference and you don't accept it, and you decide to tweak the data so that you will get what you want, you are just committing a type 1 error. And in a case where there is truly a significant difference, but you don't want that because of your paymaster, and you decide to tweak the data to show there's no difference, when a difference truly exists, the researcher is committing a type 2 error. All right? So we progress now to the test of significance. All right? And how it differs from the statistical significance. So I had mentioned to you, the statistical significance itself is the evidence that shows that the association you have done, the null hypothesis is true, or you're going to be rejecting the null hypothesis. So the statistical significance is the evidence. And the statistical significance has a cutoff, which is less than or equal to 0.05. And I'd explain to you what that 0.05 truly means, okay, based on how Ronald Fisher explained it. However, we have what they call the TOS, which is the test of significance itself. Now, every research you do or every association you do based on the hypothesis you have formulated will have a test of significance. And the type of test of significance you are going to use is dependent on the nature of the data that you're going to be comparing. Now, when we talk about nature of data, let me show us this slide, the nature of data. Now, your data itself can be a categorical data. It can be a numeric data. Now, when you say categorical data, they are data that are not numbers. And they can be nominal, they can be ordinal. Nominal simply means they don't have numbers and they are not ordered. They don't have ranking. For example, when you talk of sex, it's either a male or a female. The male is not higher than the female is not higher than the male. It's a nominal data. All right? Colors, depending on your preference. You may like a color of blue, you may like a color of black, you may like a color of green. It depends on your preference. There's no color that is higher than another color. And when it comes to these categorical data that are nominal, we represent them in frequency and percentages. I'm going to show you that, as we progress practically. So we demonstrate that in frequencies and percentages. That's why they are categorical data. All right. Now that categorical data also have the other one they call ordinal, that has an order. All right. And that order can progress. And everybody knows anywhere in the world that there is that order. It's categorical, but it has an order. Now we have educational level as an example. We know that someone that is in a postdoctoral position is higher than someone that has a PhD. And someone that has a PhD is higher than someone that has a master's. And someone that has a master's is higher than someone that has a bachelor's. So there is that ranking. Now, if you see an advert and that advert said, we are looking for a postdoctoral position, and you don't have a PhD, you cannot apply. You cannot apply because the minimum qualification for a postdoctoral position is a PhD. So meaning there's a ranking in that variable. There's ranking. You can't beat the system. You can't say, oh, I don't have a PhD now, but I have the brain of a PhD student, so you may consider me. There's no way that you will be considered for a postdoctoral position without having a PhD first. Another example for ordinal is stages of disease. Stage 1, stage 2, stage 3, sometimes mild, moderate, severe. When it comes to cases like renal failure or cancer, doctors stage these things. And when a patient is told, oh, you are in stage 1 cancer, sometimes they feel a bit relieved because they say, oh, okay, we'll do a few chemotherapy sessions and it's going to go away. The way a patient that is told you have a stage 1 cancer feels, and the way a patient that is told you have a stage 4 cancer, and when they had explained the pros and the cons for both of them, their countenance are never the same. Because when it comes to stages of disease, there is hierarchy. One is more milder than the other, while the other is more severe than the other. So for categorical variable, yes, they can be nominal, they can also be ordinal. However, the other part, which is the numerical data, which is the numbers, there are some conditions where those numbers are integers, meaning they are whole numbers. And there are some conditions where those numbers have decimals. Those numbers that are integers, whole numbers, they are called discrete. The ones that are decimals, that have decimals, are called continuous. So the reason why they are called continuous is because of their decimal nature. So for discrete, example is like number of children. You cannot have 1.5 children. Either you have one child or 2 children or 3 children. There's nothing like 1/4 children because it doesn't have decimals. Number of cars, you can't have 1.5 cars. It's either you have 1 car or 2 cars. So those are numbers, but they are discrete integer numbers. Okay? So the other one is the continuous. The continuous have decimals. We had always treated age as if age is a discrete variable. Imagine asking someone, how old are you? And the person says, oh, I am 23 years old, or I am 34 years old. Treating age as if age is discrete. Age is actually continuous. It has decimals. So if you ask someone, how old are you? And the person says, I'm 23 years old. You can only be 23 years old on your birthday. If that day is not your birthday, there's no way you can be 23 years old. You're either 23 years and 1 day, or 23 years and 1 month, or 23 years and 5 months, or 23 years and 8 months. So that's why I always encourage my students, if you're designing a questionnaire, please, when it comes to the aspect of collecting age, please put age at last birthday. Because if you don't put age at last birthday, which is a whole number discrete, there's no way that person can be 23 or 25 or 38, whatever they write there. Okay? So age is actually continuous. The same thing with weight and height. These values, when you collect them, you will see points, numbers. They are usually decimals. All right? So now that you appreciate this, we would go back to the blog part. So when it comes to this test of significance, the test of significance you use is dependent on the nature of your data. So for example, now look at this table 3, all right? The same information from the previous blog, which is the part 1. Now, if you look at this, it's the same knowledge, good and poor. It's the same COVID-19 test results, positive, negative. However, there's something new here. What is that? The chi-square. The chi-square was not in the previous one. Why? Because that previous one, I was only focusing on the evidence, which is the p-value. But for you to have the evidence, you also have to tell us the test of significance that is guiding that evidence. So the test of significance quantifies this difference, because the reason why you're doing an association, because you want to check whether a difference existed. That's the reason why you're actually doing this association. Is one of these value higher in terms of percentages and relates more to the outcome you're measuring more than the other? So the test of significance quantifies the difference. Then the p-value, which is the evidence, tells you whether you're going to accept that test of significance or reject it. All right. So the reason why we are using chi-square in this case is because we are checking for differences in percentages. So anytime you are checking for how one percentage differs from another, and why are we using percentages here? Because knowledge of COVID-19 protective behavior, it's a categorical variable. Good or poor, it's a categorical variable. All right. And COVID-19 test result is also a categorical variable, positive or negative. And when you have categorical variables, you can present them in frequency and percentages, which is what we have done. 6 is the frequency, also called counts, and 6.59 is the percentage. So because we are checking whether 19.67, which is a percentage, significantly differs from 6.59, which is also a percentage. Based on this symbol, you have your percent symbol. We are going to be using the chi-square test of significance. So anytime you are running an association based on the hypothesis you have formulated, and you're going to be checking for differences in percentages, the test of significance to use is a chi-square. That's what we usually use to confirm if a difference exists between two percentages. But looking at 4.80, it doesn't tell you anything because tests of significance, they don't have cutoff. So if you have only the chi-square, which is 4.80, you would not be able to tell whether there's evidence to reject our null hypothesis here. We will not be able to tell unless we see the p-value, which is the statistical significance, which is also our evidence. That is why when you run an association in a statistical software, it will not only generate the chi-square, it will generate the p-value. Because the software also knows that without the p-value, you will not be able to make a decision in your hypothesis because the chi-square does not have cutoff. It just gives you a number. All right. However, based on my experience, the higher the chi-square numbers, the more significant your associations will be. So meaning that if you have a chi-square value like 0 point something, you may likely have a p-value that is higher than 0.05 based on my experience. All right. So running a chi-square is because you want to check whether differences exist. Okay. So if we're going to use like an SPSS, so let's say this is our SPSS data. All right. And we want to run a chi-square using SPSS. So we have this data. Now, these are categorical data. Yes or no is categorical. I don't know. So this data, it's the COVID-19 data where you're asking them different things. And the outcome variable here is actually, that's the dependent variable here is this one. Have you accepted COVID-19 vaccine before for this particular data? Because the data is actually measuring whether they have accepted the vaccine before. So this is actually the main outcome for this data, which is the dependent variable. And whether they have accepted the COVID-19 vaccine is dependent on many other things, okay? So I want to show you, if you want to run a chi-square using SPSS, how do you do that? But first, I want to confirm if you can see the SPSS. Can someone just type yes if you can see the SPSS? Okay, all right, thank you. So if you want to run a chi-square for SPSS, it's very easy and very simple to do. Once you have your data uploaded here, like you have here, so you just come to analyze, you go to descriptive statistics, then you come to cross tabulation. So that's where you run a chi-square using SPSS. I have a video where I did all these things in Arrow, which is the 5-day training we had. So I think it's already uploaded in the YouTube page. So if you want to, know how to do chi-square in Arrow, I think that video will actually help you. Data management using our robot. For these examples, I am using SPSS, which I think is also a popular statistical software. So like I said, to run the chi-square, you go to Analyze, you go to Descriptive Statistics, then you go to Cross Tabulations. When you click your cross tabulations, sorry, let me do that again. You go to cross tabulations. I wanted to reset, okay? So when you come here, you're going to see row, you're going to see column. Column is your outcome. So you put your dependent variables in the column. Then you put your independent variables in the rows. So like I said, you can put as many independent variables you want in the rows, but you are only allowed to put just one dependent variable here, because the way you formulate the table, you would have the independent or explanatory variables on the row side, then you will have the outcome variable in the column side, like you saw in that table that I showed you. So our outcome variable in this case, I told you it is, have you accepted COVID-19 vaccine before? We put it in the outcome. Then you can choose any explanatory variable you want. Any explanatory variable, we can choose gender, we can choose age group, we can choose highest level of education, then maybe choose the first variable, maybe this other one, and put them all here. All right, it doesn't matter. Then you go to the statistics, then you choose your chi-square. Why are you choosing chi-square? Because you want to check for differences in percentages. So you choose your chi-square, that's all you do here. You continue, then you come to the cells, you're going to choose row percentages. There's column percentages, there's row percentages. Now, the reason why you're choosing row percentages, because have you accepted COVID-19 vaccine before, which is the yes and the no, those both values are inside COVID-19 vaccine acceptance. So anytime your dependent variable is not two distinct groups. For example, now, if I am doing an association where I want to check if differences exist in two countries, these are two distinct groups, or I want to check if differences exist between those living in the maybe rural area and those living in the urban area, those might be two distinct groups. I'm going to be using column percentages. So when you're doing a cross tabulations where the grouping in your outcome variable, in your dependent variable is distinct, they are different, you're going to be using column percentages. But when the dependent variable, they are not distinct, like have you accepted COVID-19 vaccine before, is one variable that has two values inside, yes and no. Another example, test result for preeclampsia, positive and negative. Test result for COVID-19, positive or negative. So these variables have their values inside that one variable. So you use row percentages. But when you're dealing with a dependent or an outcome variable that are two distinct groups, then you're going to be using column percentages. So in our own case, we are using row percentage. We continue. I think that is all you need. Then you just say, okay. Then you see it's going to generate the result for you. So we see that has COVID-19 vaccine arrived in your country? So we can see that those that said COVID-19 vaccine has arrived in their country, which is a yes, 88.1% of them had tested. All right. And if you go further, I think we did gender. So let's look at gender between male and female. So look at the male. For the males that tested for COVID-19 is 89.1%, as you can see. The males that tested for COVID-19 is 89.1%. All right, so we're doing row percentages. 10.9 plus 89.1 is 100%. 12.9 plus 87.1 is 100%. So we are doing row percentage. Like I said, the yes and the no is inside one variable, which is have you accepted COVID-19 vaccine? So the male, 89.1% have accepted COVID-19. Why? For the females, 87.1% have accepted COVID-19. So looking at 89.1 and looking at 87.1, we can say, more males tested for COVID-19 than females. After all, you're seeing 89.1 and 87.1. I can go around screaming, oh, males are testing better for COVID-19 than females. Males are testing better for COVID-19 than females. And someone comes to you and say, really? What is your evidence? And you're like, well, that's what my percentage is showing. But in terms of research, it's not enough. Differences in percentages are not enough. You have to show evidence using the test of significance as also the statistical significance value, which is the p-value. So now we go down to the chi-square test. Our chi-square test is 0.344, and our p-value is 0.557, which is higher than 0.05. So what is this showing us? There's no evidence. There's no evidence that males are testing better than females. You see why evidence is important? Because if we are focusing only on the percentages, we will be making a lot of assumptions that are not true. Imagine someone saying, oh, males are testing better than female, but our evidence is saying that it is not true. Meaning that the difference between the test for males and female is not high enough. 89.1 is not higher than 87.1 in that sense. The percentage difference is very small. That's why the evidence is showing that there's truly no marked significant difference. So if we have a null hypothesis here that says there's no significant difference between gender and COVID-19 vaccine acceptance, COVID-19 vaccine acceptance, based on our significant value here, we can say that there's no difference. So we'll have to accept our null hypothesis based on the evidence. That's why the chi-square test, which we use because we are checking for differences in percentages, and the p-value that gives us the cutoff, all right, is giving us the evidence. So like I mentioned, looking at 0.344, we will not be able to tell whether a difference exists or not until we see our p-value. That's why I said when you run the test of significance, it will generate the chi-square, and it will also generate the evidence, which is the p-value. All right, it's here. So also note that it is generating a Fisher's exact test. So that Fisher's exact test is also a test that is done when you're checking for differences in percentages. But you only use Fisher's exact test if one of the values in your count is less than 5. So looking at this association we have done now, we have 17, 139, 27, 182. None of this count is less than 5 in our association. So we will stick with our Pearson's chi-square and also our two-sided p-value. However, if we had one of the values here that is less than 5, maybe instead of 17, we had 1. Instead of maybe 139, we had 3. If we had a value here that is less than 5, we wouldn't have considered our chi-square. We would have used the Fisher's exact test. And note that the Fisher's exact test, it's a special type of p-value, special type of evidence. It is not a chi-square, because I've seen instances where people will draw a table like this and they do an association and they say, oh, they use the Fisher's exact p. They will give a chi-square value and now give a Fisher's exact p-value. That is wrong. If you're using a Fisher's exact test, it's a special type of p-value that adjusts for small numbers. It doesn't have a chi-square. Chi-square is when you have all your counts are greater than 5. So that's how it works. Now, you have the two-sided, you have the one-sided. All right. So for us in the field of epidemiology, public health and the rest of them, when we do associations or when we do research, our interest is usually in both sides. In other words, have you accepted COVID-19 vaccine before? Now, the COVID-19 vaccine has a yes and a no. We are interested in both sides. We are interested in the yes, we're interested in the no. So our research is usually interested in the two sides. Those that have tested, those that have accepted the vaccine and those that have not accepted the vaccine. That's why we use two-sided, because we're interested in the yes and we're interested in the no, depending on our interest and depending on the researcher's interest. If your interest is in those that did not accept, you focus on the no. If your interest is in those that are accepted, you focus on the yes, but it's usually two-sided both ways. All right, so let's move on back to the blog. So I was trying to show us practically how to actually run this association. All right, now, even if you're going to use another statistical software like EpiInfo, you will still see that it's going to show you the chi-square, degree of freedom, and also the probability, which is the p-value. Meaning that anytime the chi-square is generated, it will generate the p-value alongside, because you will not be able to make a decision whether to accept or reject your null hypothesis without the probability or the p-value, because the p-value has a cutoff, but the chi-square does not have a cutoff. That's why the statistical software will bring out both. You have to put the test of significance, then you can now use the p-value to make a decision whether to accept or reject the null hypothesis. All right. So if I use like EpiInfo to actually do this, let me see if I can show you how to use EpiInfo to do this quickly. For EpiInfo, you go to analyze the data. Then you come here, which is the read, so that you can choose the data that you want to analyze. The database is in Excel. I put the data in Excel. So I come to Microsoft Excel, I browse so that I can find where I have that data, which is on the desktop. I have the data on the desktop in this folder, practice data. So I've chosen the data, I open it, and I said, okay. So the data is going to load for me here, sheet 1, then I say, okay. So the data loads here, then I can run, it's loaded, I can run the association. So to run association in EpiInfo, you just go to tables, just come to tables, and the exposure is anything, maybe our age group. Then the outcome is the COVID-19 vaccine itself. Where's that outcome? Have you accepted COVID-19 vaccine before? Yeah, so this is our outcome. Then we just say, okay, and it will show you the cross tabulation. So you see, it's the same thing. So it's showing you the different age group and which one have accepted COVID-19 before. If you come here, you see, it's giving us the chi-square and the p-value. Now, how do you interpret this result? You look for the prevalence. So one thing with EpiInfo, it gives you the row percentage, it gives you the column percentage. I've tried to learn how to choose one, but I don't think it will give you both. But you have to appreciate the fact that it is row percentages that you would be using, not column percentages, like I explained to you. Now, how do you interpret this result? The fastest way is, if your interest is in the yes, you go to the yes column and you look for the age group that have the highest percentage. That age group that has the highest prevalence for the accepting vaccination is the age group that has this evidence. So if we look at 18 to 29, 80, 84.7, 93, 100, and 100. So in this case, we can see this is 100, this is 100, but this is lower. So from this result, you can see that age group, those that are 50 years and above, accepted more COVID-19. For those that are 50 years and above, all of them accepted COVID-19. So that's to tell you that the statistical significance, which is the evidence, is in this age group, 50 years and above, which shows that for the age group, those that are 50 years and above, we significantly or statistically significantly accept the vaccination for COVID-19 compared to those that are 30 to 49 or those that are younger. All right, as you can see. So the older people significantly accepted the vaccination much more than the younger people. Even those that are 30 to 49 accepted the vaccine more than even those that are 18 years to 29. So it shows you that the older they are, the more chances that they are going to accept the COVID-19. Okay, so let's go back to our blog. So I've already shown you all this. Now, I've already told you for the Fisher's exact test, why or when do you use it? Like if you look at this table now, you can see that we have 4 here. We have 87 here. We have 14 here. We have 47. We would not be using chi-square and p-value. All right, like you saw here. Chi-square and p-value, no. We would only use a Fisher's exact test, which is a type of a p-value. Why? Because we have a count that is less than 5. All right. And let me say this before I forget. Anytime you are representing your result in a publication, I will show you some examples from my own work. Appreciate the fact that the test of significance is what is showing the difference, not the p-value. Because I've seen cases where people will represent their tables, they will only put the p-value. They will not put the exact test of significance. The fact that you're testing for differences in percentages, please put your chi-square. Then at the side, you can now put the evidence that gives you a clue whether you're going to accept or reject the null hypothesis. So Fisher's exact P for small counts, small numbers. All right. Yeah. So we have different types of test of significance, different depending on what you're associating. So I had said that when you are associating percentages, differences in percentages, you're going to be using the chi-square. If you have values that are less than 5, you're going to be using the Fisher's exact. Now, there's something they call parametric analysis and non-parametric analysis. So when you are running, you are collecting your data, we usually encourage persons to collect their data using what they call probability sampling. Now, probability sampling is things like simple random sampling, cluster sampling, systematic sampling. So when you follow a sampling process, which gives every participant an equal chance of being selected, there's a good chance that your data will be normally distributed because you use the sampling. All right, you did random, some form of random or the other. So your data will be normally distributed because you gave everyone equal chance of being selected. But there are instances where you don't bother. You use like convenient sampling. Anybody you see, you just choose for that study. You don't bother using any form of sampling. You just choose them as they come, or you just choose them anyhow without following any process. So in cases like that, oftentimes that data may be favoring one group over the other. A very good example I can give you is, imagine you are a consultant in a teaching hospital and you're doing a study where you want to know the average pay, of a staff in that teaching hospital. And because you're a consultant, you administer the questionnaires to your friends. You did convenient sampling. You gave the questionnaire to your friends, and your friends will most likely be consultants and professors. You see, you didn't give to the warders. You didn't give to the lab technicians. You didn't give to the medical record keepers. You just gave your friends. So you find out that when you now run a mean of that data, average income, average wage, it will be as if your hospital is the highest paid hospital in that region. That data is skewed. Why? Because you only conveniently focus on one group of people. So in instances like that, you would not be using parametric, because parametric will be measuring means. you'll be using non-parametric, which will measure medians, which will give you a more appropriate result, because medians will not be looking at extremes, but means would be. All right. So that's why it's usually recommended that before you make a decision whether you're going to be running parametric or non-parametric, you're going to be doing test of normality for that data. All right. So how do you do test of normality? If I use SPSS to show you that, all right, it's very easy to do. And note that you only do normality for continuous variables. You don't do normality for categorical variables like this no and this yes and all these females, even this group age, no. Education, no. Education, no. You know, you only focus on the numbers. You only focus on the numbers. So to run normality for our continuous variable to see whether we are going to be using parametric or non-parametric, how do you do that in SPSS? You go to Analyze, you go to Descriptive Statistics, you go to Explore. So when you get to Explore, you choose your continuous variable. Like I said, normality is only done on continuous variable. So our continuous variables here are like weight. You can tell they are continuous because you'll be seeing this ladder symbol on them, which shows continuous, like a ladder. But the ones that show these cycle boxes, they are categorical because the categorical values differ. You may have male, you may have female. So the male can be red, the female can be blue. Then did not decide maybe A. You know, that's why they use those symbols. But anytime you see this ladder symbol, you know, more like one song we sing in Nigeria, follow the ladder, you know, follow the ladder. You know, so so this ladder sign is for continuous variable. So you choose your continuous variable, you know, and you put it in this place, the dependent list. Then you come to, I think, plots. Yes, so you come to plot and choose normality plots and you continue. And I think that is it. Then you just say okay. So once you say okay, it's going to give you the so you have you can either use Shapiro-Wilk or Kolmogorov, Spinoff. Both of them do the same thing for the test of normality. So looking at our continuous variable, you can see that all the p-values here are statistically significant. The weight, the height, the BMI, the age, they are all statistically significant. And what does that mean? Simple. It means our weight, our height, our BMI, and our age, they all significantly deviate from normality. So all these are data, they are skewed. This data is skewed. All right. And why is it skewed? It's because I actually formulated this data. I didn't collect it from the field. You know, it's actually a data that I formulated for practice purposes. So it's understandable why it will be skewed. All right. So you see, they are all skewed. So when you run your normality and you have a significant p-value, it just tells you your data significantly deviates from normality. And the moment your data significantly deviates from normality, it means you're not going to be using parametric. You're going to be using non-parametric. So instead of calculating mean, you're going to be calculating median. So the decision whether to use parametric or non-parametric is dependent on that test of normality. You don't just decide what you use, okay? So for the parametric, our focus is for the means. For the non-parametric, our focus is the median. So if you're running an association where you're checking for differences in two means, all right, two independent means. Now in this case, independent simply means the two values are independent of each other. For example, now, if they have accepted COVID-19 test, if they've accepted COVID-19 vaccine, all right, so accepting COVID-19 vaccine, that's independent because those that said yes and those that said no are independent. So you now run mean age. We can run mean age between the yes and the no. So that would be independent student t-test. Why is it student t-test? Anytime you're checking for differences in two means that are independent, you use independent student t-test. That's what is used for checking differences in two means. However, if you're checking for differences in two means, but those two categories are not independent, they are dependent. Like, for example, you come to an environment, where you have children that are malnourished. You take their weight, you provide an intervention by providing food, teaching their parents how to feed them and all that. And after 6 months, you come back to the same environment and you take the weight again. And now you want to check the mean weight before the intervention and after the intervention. So you're still checking for differences in two means, but it is the same population, but at two different times. Then you'll be using dependent or paired student t-test. But if it's independent, then you'll be using independent student t-test. However, if you're checking for differences in three or more means, then you're using analysis of variance, ANOVA. Three or more means is analysis of variance. All right. But if you now observe your data is skewed, you now move to non-parametric. So if you're checking for differences in two medians, you're using Mann-Whitney. If you're checking for differences in three or more medians, you're using Kruskal-Wallis. So that is how this works. So let me show us practically how this is done. So our continuous variable, we have age here, and we want to look at mean age among those that took the vaccine. Not that. Let's look at mean age across gender. Let's do mean age across gender because we have male and female, so we can check this respondent between male and female, which group is older. So how do you do that? You come to analyze, descriptive statistics. Compare means, not descriptive statistics now. Sorry, that is for chi-square. Compare means. You come to independent sample t-test, not paired now, it's independent. So you click your independent sample t-test. Then you put the group, which is the gender. And the gender, let me show us something, because it will ask you, what numbers did you use to represent that variable? So for males is 1, for female is 2. How would you know that? You come here. If you click here, it will transform it to show you what the number is. If you click here, it will transform. So based on this transformation, you can see that male is 1, 2 is female, because it's going to ask you. So let's go back. Analyze, descriptive statistics. Compare means, independent sample t-test. Then your grouping is the gender. We put it here. Define group. It is 1 and 2. Continue. Then our test variable. So it's the continuous we put here. So let's put our age continuous here. I think that is all. Then you say okay. Then when you say okay, this is the value. So the mean age for male is 33.78. The mean age for female is 34.55. So if we're stating a null hypothesis here, it would be there's no significant difference between the gender and age. But 34 and 33, is that difference statistically significant? We will look at our test of significance and also the p-value. What's the test of significance? The student t-test. So the student t-test here is 0.577. All right, please ignore the minus when you're putting it in your table. So 0.577, and the two-tail p-value is 0.567. All right, so that's the p-value. So this p-value is higher than 0.05. So this p-value is telling us that there is no significant difference between age between male and female. We can even do for gender. We go back. Instead of age, sorry, I said gender, we can do for BMI. BMI is also a continuous variable. We can do for BMI and C. So BMI, the BMI for both sexes is almost the same. So the P will definitely not be significant. You're seeing it 0.276 as 276, yeah, and the t-test is 1.09. So it's not significant. So in terms of ANOVA, you have to do it for 3. Something that has 3 groups or more would now be ANOVA. So for ANOVA, the one that has 3 groups is highest level of education, as you can see. So let us run a frequency, just a frequency for highest level of education to confirm that it has more than 2 groups. So analyze descriptive statistics frequency. Reset. So let's choose just to know how many categories it has. Highest level of education, put it here and say okay. So you see it has more than 2 categories. So this can fit very well in ANOVA. So we can do age against highest level of education. Is just for practice. So we go to analyze, compare means, but this time will be ANOVA. So we choose the highest level of education. You don't have to decide whether it's 1 or 2 in ANOVA. You just put it there, then put your continuous variable. So this time is age. Are you choosing any other thing? I don't think so. I think descriptive, yes, you choose descriptive so that to show you the mean for each, the mean age for each education. So you continue. I think that's all. You say okay. So it has shown you, as you can see, the different ages. They are not so far apart from each other. PhD is 33, diploma is 32, not so apart. So that's why you see the p-value is not significant. So we can truly say that the age did not differ in terms of education, to show you that people are progressing with their school. As they are finishing this one, they are entering another. There's no gap in schooling, which is why you can see that the age did not differ in terms of their educational level, as you can see. So the F test is actually ANOVA. So either you call it analysis of variance or you call it F test. So it's also called F statistics or F test, while the other one is called T test. All right. So in terms of, so this is for parametric. So in terms of non-parametric, you come to analyze, then you go to non-parametric tests. Then you come to independent sample. So when you come here, you can actually choose the gender. Gender is for 2. Then you can choose your continuous variable. So this one, because it is 2 groups, continuous, and it is median, it will give you Mann-Whitney. So the significance is 0.155. So you retain the null hypothesis. It's even giving you a decision. Why? Because the p-value is not significant. You retain the null hypothesis. So you see it is doing Mann-Whitney. Why? Because you're testing differences in 2 groups. So if we now do for 3 groups, we go back to non-parametric. If we remove the gender and put something that has more than 2 groups, which is the highest level of education we run, you will see that it will give you Kruskal-Wallis instead. So Mann-Whitney is for 2 groups, Kruskal-Wallis is for 3 or more groups for non-parametric. But for parametric, student t-test is for 2 means, while analysis of variance is for 3 or more means. So 0.233 is way above 0.05. So it says retain the null hypothesis is not statistically significant. So that is how this works. Now, I know that a lot of us have heard of post hoc analysis. Now, post hoc analysis is only done when you have a statistically significant ANOVA, actually. If you don't have a statistically significant ANOVA, you don't run a post hoc analysis. A post hoc simply means after analysis. So because when you run ANOVA, like let me show you what we did. When you run ANOVA, all right, you see that it showed you which mean is highest. Like if you look at these means now, the mean that is highest here is bachelor, which is 35.61, is higher than the rest, but it doesn't really matter now because it's not statistically significant. So we can say age difference does not matter here. However, if we had a statistically significant ANOVA here, we would have run the post hoc. Why are we running the post hoc? The post hoc will tell you which 2 groups has more significant difference. Let me show you. Now, if you go to analyze, you go to the compare means, you go to one-way ANOVA. This is the post hoc. So post hoc has different. We have the least significant different LSD, which is popular. Turkey is also popular. Bonfereni is also popular. But for me, I usually do Turkey or Bonfereni or else LSD. But there are many others, but they are not so popular. All right, so let's just choose LSD as our post hoc. I think that is all you do. Then you continue. I think that's all. So see what it's doing now. So it will be testing them one after the other. All right. So in this case now, it is running PhD against all this, running masters against all this, running bachelors against all this, running diploma against all this, running below diploma against all this. If it was actually significant in the first place, you will be able to tell which of this group is more significant than the other. But here just gives you a general overview. But here it will break them down into little bits to be able to tell you which group here is more significant than the other. So that's what the post hoc does, but it's usually done when you have a significant ANOVA. Yeah, I think that is basically it. So we would wrap up with some work I have done, which I wanted to use it to explain the confidence interval before we wrap up. So this is a publication just recent. I think a few days ago, was on the 22nd of October. This is like one of the publications from my PhD. So I will use the tables that I did and analyzed to actually explain some concepts. So let me use this one instead, the COVID-19 vaccine data that we published. Let me look for the table. So this is the paper. So let's go to the table. I want to use it to show you about confidence interval. So, there has been this debate of whether to use p-value or whether to use confidence interval. Well, for now, you can actually have both, especially when you are running logistic regression. I have a whole webinar on logistic regression, so I don't want to really go there now, okay? I have a whole webinar where I talked about logistic regression, but I just want to show you about the confidence interval. Now, I remember a few years ago, a doctor brought some analysis, to me. And in those analyses, he had some confidence intervals. And when I looked at the confidence intervals, I was looking at the confidence intervals and I was looking at the p-value. And I told him that these p-values are not correct. And the doctor looked at me and he was shocked. He said, how did you know that? I now laughed. I said, yes, I know, because I've been doing these things for years. And because I understand the principles behind confidence interval. That's how I knew. And I asked him, why did you guesstimate? I mean, is it that you can't find a statistician to run this analysis for you instead of just guesstimating p-values and assume nobody will know? All right. So you can actually use your confidence interval in place of the p-value. How does it work? Now, a confidence interval gives you a range. All right. It's more like, in this case now, you run an adjusted odds ratio after you have done the chi-square. The values that are statistically significant in the chi-square, you move them in the bivariant. The variables that are statistically significant in the bivariant, you move them in the multivariant. All right. So if you look at this, the crude here says 2.02. The reference is the no, meaning that you are interested in the yes. So this crude odds ratio is simply telling us that those that have done COVID-19 test before are 2.02 times more likely to accept the COVID-19 vaccine. All right. But if you look at this confidence interval, you will see is 1.07 to 3.79. There's no one in between. There's no one in between 1.07 and 3.79. That's why it is statistically significant. If you look at the adjusted, it is 17.69, 1.21 to 256, 0.91. There is no one in between one. So 1.21 is after one. So anytime you have a confidence interval and there's no one in between, it will most likely be significant. All right. Now look at this one, 5.8727. There's no one in between. The one is before 5.87. But look at this one. This is not significant. See, there's a 1. After 0.33, you will get to 1. Before 1 point something, before you get to 30.55. So there's a 1 in between the minimum and the maximum here. That's why this p-value is not significant. If you look at this one, there's a 1 between 0.009, So you will get to 1 first before you get to 1.07. You see, it's not significant. If you look at this one, 0.031, you will get to 1 first before you go to 2.82. You see, it's not significant. So anytime you have a confidence interval and there's no 1 inside, it will most likely be significant. Look at this one, 0.043 to 0.214. There's no 1. 1 will come after 0.214. 0.046 to 0.213. There's no 1. 1 will come after 0.213. So the confidence, sometimes they had said, okay, instead of using the p-value, why not use the confidence interval? Yes, it can still work. So I'm telling you the principle behind the confidence interval. So if I see a confidence interval that does not have 1, between the minimum and the maximum, I can tell you that it will most likely be statistically significant. So that is how the confidence interval can be used also to represent your p-value, if that is what you want. But there's no harm if you have both of them there. Really, there's no paper that is going to say, oh, take one out. No, they will still publish it like that. Now, we don't usually have confidence interval in chi-square. But we have it when you run odds ratio. Yeah, I think that is basically it. I have covered mostly the things I wanted to cover today. So I think we are wrapping up here. Thank you very much. So I think that is it. Yes, I've covered everything. So it's now a few minutes for your questions. So I'll be looking at the questions in the chat first quickly, then you can unmute yourself and ask before we wrap up. Someone asks, in fact, the values I got from this webinar cannot be quantified. I used scaring of, but my brain is open, but do endeavor to share. Yes, we will share the recording there. Please pardon me. I have to look at the chat quickly. Someone said I should come again with the type 1 and the type 2 error. I think I would appreciate it if you can watch the recording, because of time. I explained it in details. I like the example. I have a doctoral mindset. Okay. Okay. Yeah. I think any other question? What's the difference between the p-value and confidence interval? I've actually explained that now. Yeah, the degrees of freedom. It's actually a formula that says the column -1 times the row -1. It just tells you the number of boxes. So let me just explain that degree of freedom quickly. It's not a rocket science. Someone is writing on the on the screen. Let me erase that quickly. So the degree of freedom is not rocket science. It just gives you a clue how many boxes are interacting in your association. So let me just show you that quickly. Now look at this. Look at this. How many boxes do you have here that are interacting? Is actually 4. 1, 2, 3, 4. Positive, good. Positive, poor. Negative, good. Negative, poor. So 4 boxes are interacting here. So if I'm to calculate the degree of freedom here, the formula is column -1 times row -1. So how many columns are interacting here is 2 columns, positive and negative. 2 minus 1 times how many rows are interacting here is 2, good and poor. 2 minus 1. So 2 minus 1 is 1 times 2 minus 1 is 1. So 1 times 1 is 1. So the degree of freedom here is 1. So if you write a degree of freedom of 1 for me, in my head, I'm like, okay, what generated the chi-square and the p-value is actually a table that has 2 columns and 2 rows. Something like that. Yeah. So that's really what we use the degree of freedom for. It just gives you a clue in your head. How many rows and how many columns are actually interacting in the association that you do. So when you have more degree of freedom, it gives me a clue in my head that you have more columns. Columns are usually 2, but you have more rows that are interacting in your association. Sometimes you can have more than 2 columns, yes, but oftentimes your outcome variables are usually 2 values. So I hope I was able to explain that. Okay, DF is degree of freedom. Yeah, degree of freedom. Okay, everybody's asking of degree of freedom. I'm sorry, I didn't explain that. Yes, further knowledge on SPSS, you can watch other webinars. If I dummy a continuous variable and run the normality test, is it acceptable? I don't know what that means, but you run normality tests on continuous variables only. You run normality tests on continuous variables only. Yes, so if your age is not normally distributed, you are going to run median. Yes, so if I run a mean, it's just for practice sake, but I'm teaching you the right practice. So if you are done your normality test and it is skewed, please use median instead of mean. Yes, the recording will be shared. Okay, yes. So I would look at doing short webinars so that we take each of these things one after the other. The crude odds ratio and the adjusted odds ratio. I think I would appreciate for the crude and adjusted odds ratio, I would appreciate you watch the webinar. Just a second, I'm trying to answer your questions. Please be patient with me before you go. If you have a question, trust me, I'm going to address all of your questions. But let me take what is in the chat box and try to respond before I take the verbal question. So someone is asking about the crude odds ratio. So please let me. I had shared the webinar on logistic regression. Please, once you go, so I am dropping that webinar here, the one I did on logistic regression. Please, there I explained everything about crude and adjusted odds ratio and the rest of them. So I'm pasting the webinar there. So you will see other related videos. I think I had shared other related webinar in the email I sent, but let me just drop them here just in case some of you did not actually get that. So I'm dropping them here as well, the other webinars we had done. So let me proceed with the questions on the chat. Sorry, I think I have a few more. I had explained the Fisher's adjusted odds ratio. I had explained that. The type 1 error, I had explained that. I will share the recording. The Fisher's exact, I had explained that. I will share the recording because of time. The post-hoc analysis in non-parametric, I think the post-hoc analysis is recommended for the significant ANOVA. No, we are not allowed to say males were more than females without the p-values. It is the p-value that gives you evidence whether males are higher than females, irrespective of the percentage difference that is there. You need an evidence to say whether a statistical significant difference truly exists. Okay. Yes, the materials will be shared. Confidence interval, one between values to show significant. Okay. Someone is asking about the confidence interval. I know I had actually explained that, but let me show that again briefly. So what I was saying is the confidence interval, you can actually use it as a clue in determining whether you have a significant p-value or not. All right, and the confidence interval is generated when you run like the logistic regression, okay? It doesn't come out when you run chi-square. All right, so like you can see now, we have a confidence interval here, 1.07 to 3.79. If you check this minimum and maximum range, you will not see a 1 in between this, meaning you have 1.01, 1.0, you have 1, you will have 1.06 before you even have 1.07. So there's no 1 in between these ranges. 1.07 is after 1. 1.21 is after 1. That's why it's significant. All right. 2.68 is actually after 1. So there's no 1 between the minimum and the maximum. But if you look at this, 0.39 is before 1. You will get to 1 before you get to 2, get to 3, and get to 43. You see, the p-value is not significant. If you look at 0.33, it is before 1, meaning 0.33, 0.3435, you get to 1 before you now progress to 30.55. That's why the p-value is not significant. So anytime you have a 1 between the minimum and the maximum, your p-value will most likely not be significant. Okay, so that is it. Yes, I would, for parametric and non-parametric. I don't know if maybe I can find a simplified literature for parametric or non-parametric, but I know I had tried to explain it in a very simple form. Okay, I think we have finished with the questions. So let me unmute participants so that you can ask your questions. You can unmute yourself now and ask. I think I've given you permission to unmute yourself and ask. So let's take Tongu. Tongu Allison. Let's
thank
take
you,
it first.
Doctor.
Yeah,
Thank you very much, Doctor and colleagues. I think I have learned a lot today.
thank you.
I am a PhD student from Uganda, Mathers University in Uganda. And my study is going to be a comparative study comparing the impact of digital uptake on the management of public and private secondary schools in West Nile. Now, my issue is, I think I will be running a t-test because I have two distinct groups from public and private sector. But then the questionnaire may cover collect data from students, teachers, and head teachers. Now, is it advisable for me to run some tests there, and which one should I run, if possible? Thank you very much.
Yeah, so like I said, the test that you're going to be running will depend on the nature of the data you're collecting. It's called scale of measurement. So are you comparing differences in means? If you're comparing differences in means in a variable between the public and the private, maybe you're comparing differences in knowledge score, which may give you a mean, or which you will use a median, all right? Or you're comparing differences in BMI between, or any other continuous variable, then yes, t-test is applicable because public and private, they are independent. So t-test is only used when you are checking for differences in means. So I would ask you, are you checking for differences in means? Is that why you want to run t-test?
Yeah, it will be differences in mean.
So if it's differences in two means, then t-test, you can do independent student t-test. Yes.
Thank you very much.
Thank you. Yeah, Godwin.
Thank you, Doc, for that insightful presentation. Indeed, I've also learned a lot today. And the only thing that is still, a bit confusing to me is the difference between statistical tests and then the test of significance. I'm still not so clear about the difference.
Okay.
Yes.
All right.
So if you could just throw more light. Thank you so much.
All right. So the difference is, the test of significance and the statistical significance. All right. The statistical significance itself is the evidence that is backing the test of significance. So the test of significance, there are many, depending on the hypothesis or the association you are running. Like I said, if you want to compare differences in percentages, you use the chi-square. That's the test of significance. If you want to compare differences in two means, you use the student t-test. 3 or more means, you use the ANOVA. Those are tests of significance. But every test of significance you run will generate one statistical significance, which is the p-value. So the p-value is there to give you a clue on what your test of significance is saying. Like I said, the test of significance value doesn't have a cutoff. It doesn't have a range. So if you run a chi-square and your chi-square gives you 4.35, if you don't see the p-value close to it, you won't be able to tell whether you accept or reject your null hypothesis. So that's the difference. So the test of significance is the test that helps you quantify the difference you are measuring. But the statistical significance is the evidence that helps you accept or reject that test of significance. I don't know if that is clear.
Yeah, that's clear. Thank you so much, Doc.
Okay. Yeah. Thank you, Ibrahim.
Yes. Well, sir, thank you for the wonderful presentation. I really enjoyed and I learned a lot. Thank you very much, sir.
Thank
But
you.
because of the presentation, there are explanation on the type 1 and type 2 error. I begin to understand, but later on I miss on the road. So I need more clarification on type 1 and type 2
and
error.
type 2. Okay. All right. So, however, I will share the recording, and I am hoping that when you watch the recording, you will get it clear. But let me just explain it again. Okay.
Thank you.
So in a lay sense, for example, now you are doing a study, all right, and the example I gave, which is whether they would test positive or negative for COVID-19, but they wanted to check whether the knowledge they have would influence whether they would test positive or negative. So you feel, oh, those that have better knowledge, they will protect themselves better. So when they test, it will most likely be negative. All right. So you formulated a null hypothesis, and your null hypothesis says there's no statistical significant difference between their knowledge and whether they would test positive or negative for COVID. You did the research, okay, but your result did not show there was a statistical significant difference. So when you did the association, your P was showing like 0.950. 0.950 is of course higher than 0.05, which is the cutoff. So ordinarily, you should accept your null hypothesis, because your p-value is not significant. You should accept your null hypothesis that says there's no significant difference. But you as the researcher, you didn't like the result. You wanted a statistical significant difference by all means. So what did you do? You went to adjust the data. When you now adjusted the data and reanalyzed it, you now got a statistical significant difference. So what did that means now? It means it means now that you will now reject your null hypothesis. So a type 1 error is when you reject your null hypothesis, when your null hypothesis is true. So your null hypothesis is actually true, but you rejected it because you did some p-hacking, you did some adjustment just to have a significant difference. When truly your data did not show a significant difference, you should have just taken that result in peace. So that is for type 1 error. So type 2 error is when your result actually showed a statistical significant difference. And I use the drug company because this is what will give you a lot of clarity in explaining that. The drug showed that there was a statistical significant side effect. That is what your lab work showed. There was a statistical significant side effect. But the funders for that research said, no, we don't want that result. It may not help us sell the drug. So what did you do? You adjusted your lab reagent and all that. And you now did it in such a way now, it now showed that there was no statistical significant difference anymore. So you should have rejected your null hypothesis. But because you've adjusted your result, you now fail to reject your null hypothesis, accepting your null hypothesis when your null hypothesis was not true, because it showed significant side effect, but you had adjusted it so that it will show no significant difference, so that you will accept your null hypothesis. So in that case, you had committed a type 2 error.
All right. Thank you so very much, sir.
All right. Thank you. Yeah. Thank you. Yeah, Farouk, before we go to Catherine. Yeah.
Yes. Thank you so much, Doctor. God bless you for the work you are doing.
Thank you. Yeah.
So my question is on the test of normality.
Yes.
I've collected data and I want to know whether the test of normality should be done for all the variables before I can go and do go ahead and do the analysis. And my second question is on the p-value. I've seen several published papers where they will collect the data, they will do the descriptive statistics and say that maybe 40% were male, or between the certain age group or children, this particular age group, there are more of them than the other age group, and they don't tell you their the level of significance. I want to be allowed to do that because I've seen in some newspapers.
It is not allowed, because when you do that, you are providing an error. You know, like I gave the example of the law court. The only reason in the law where they would declare somebody guilty or innocent is not what the person says. It's not how the judge feels. It's based on evidence. The judge may feel like, oh, I need to let this person go, but the evidence didn't say so. And the judge will not let the person go. So it's not about how you feel. You may feel that, oh, males are higher than female. Of course, you may feel that way because you're looking at the percentages, it's showing that. But the evidence does not show that. The evidence, which is the p-value, shows that a significant difference does not exist. So even if one percentage is slightly higher than the other, it means there is no significant difference. You understand? So it's based on evidence. So I know that sometimes students formulate a sentence in this way. The associations show that males the associations show that males are higher, than females. However, these findings is not statistically significant. I know I've seen, but it's not really necessary. If it's not statistically significant, there's no difference. So there's no need. That's why in good practice, when you have associated tables, you focus more on those values that show the statistical significant difference, because that is what they really want to see. For those that didn't show a statistical significant difference, they just encourage you not to lay more emphasis on that and flood your work with many words that are not very relevant. So that is for the first one. Now the second one, which is the normality, yes, you run normality for all your continuous variable, all, but normality is not run for categorical. All the variables that have numbers, you run normality for them. And for those that are skewed, use median. Those that are skewed, that means those that have continuous variables with p-values that are less than 0.05. It means those variables significantly deviate from normality, right? So for those values that the normality test shows significant p-value, it means you're going to use median. But for those that the normality showed non-significant p-values, you are going to use means. Yes. So you run normality for all your continuous variable. Yes.
Thank you.
Thank you. Catherine.
Good evening, Doctor and everybody.
Yeah, good
now,
evening.
I want to take you back to type 1 and type 2, and I know you have explained thoroughly when you're clarifying for Farouk, but then I am just thinking on type 1, it's you as the data analyst who doesn't like the outcome. But is there a case that really justifies one to to really stick to use the type 1, leave alone you just not liking? I want maybe there's a case reason why you could use that apart from you not liking what you have seen.
Yeah, it's a lot of early career researchers feel that if they don't have a statistical significant difference in their hypothesis, they may likely struggle to publish it. They feel that most journals would like to publish results that are statistically significant, but that's not true. It's your findings. You should just present it the way you found it. That's like, oh, if it shows that there's no significant difference, maybe the journals will feel that the study is not relevant. So that's why oftentimes people commit a type 1 error, because they feel it will get their paper published faster.
Okay. So in essence, let's just say there's no justification.
Yes, there's no justification. If your
Fantastic.
association, if your association did not show a statistical significant difference, okay, then present it that way. However, let me say this, now that you mentioned it, oftentimes the statistical significant difference that you did not see, meaning that your association did not show a statistical significant difference. Sometimes it may not be that a statistical significant difference does not exist. It's just that the power is small. You know, the power is small, meaning that the researcher probably didn't calculate an adequate sample size. They just guesstimated the sample size that they want to use. They say, oh, let me just use 100 or let me just use 200. So that number you guesstimated does not have enough power to show a statistical significant difference if one truly exists in that data that you're analyzing. So sometimes the researcher may have caused that error by using a smaller sample size that doesn't have adequate power. So that way it will look like your null hypothesis is true. You now begin to commit a type 1 error. So instead of committing a type 1 error, ensure that you calculate your sample size well so that whatever minimum sample size you are using is adequate to truly show a statistical significant difference if one truly exists. So I did a whole webinar on sample size determination and on power. So anyone that is interested in that webinar should also watch it. I have also shared it, but let me just share it again. Yes. Thank you.
Right. Thank you.
Yeah. So, Afolabi, Dr. Afolabi. Yeah.
Doctor, I so much enjoy your lectures. So fantastic, very
Thank
practical. You are a teacher,
Thank you.
truly a teacher, and
Thank
you are
you.
the results at your fingertips.
Thank you.
So I want you to really go over parametric and non-parametric. Then the second one is I want to buttress that issue of your type 1 error. That at times the variables that are used to proxy either dependent variable or independent variable also results to that too. Particularly we use this most of the time, we use this secondary data. So instead of you now committing type 1 error, why not go back to your data and then collect more, like you have said. Collect more now, or expand the variables that you use to proxy the dependent variable and independent variable. For example, if you are in our own area accounting, if you are talking about administrative costs, using administrative cost proxy against the total cost, you will see that administrative cost is very, very small compared to total cost. So there is no way to see. And for you to now manipulating that is significant, then you are saying that administrative cost is bigger. It's even more than the cost of sales.
Yeah.
So there is your analysis of type 1, and it's a very big problem because most of the researchers, when you are, even including myself, when I have it not significant, it was like a wasted effort. But what I usually discover now is that I move back. I move back to see what have I used to proxy what have I used to proxy the dependent variable and the independent variable. Are they really significant when you talk in terms of the overall items involved in that? But most of the time, you even see your adjusted R square or your R square. By the time you say you go and do the legal thing, you will see that your R square and the adjusted R square will just open yash, and it will become yes. Thank you so much. I want you to explain the area of this. No, I want to. There are certain things you have parametric and that is very practical and technical. I want to go back.
Okay. All right, thank you. So what I said about the parametric and non-parametric is all about our data being skewed or normally distributed. Like we are told in research, and like I mentioned earlier on, that research is a systematic process. Systematic process simply means that you have to follow a process, a pattern, a guideline, a standard operating procedure. And they have told us in research, when you want to select your population, you don't just choose them as you like. You know, you don't just choose them conveniently. You follow a systematic process. Either you're doing a simple random sampling where you have a sampling frame of all the potential participants and you randomly pick the number you will use, you know, or you're doing a cluster sampling where you have all the cluster and you use sample random sampling to choose the number of cluster you need, you know, or stratified where you stratify them based on homogeneous group. Those that are male, those that are female, you randomly pick from male, randomly pick from, no, so you have to follow a probability process. So when you follow those probability process to select this sample, the chances that you have given every participant an equal chance of being selected is there. And the chances that your data will be normally distributed is also there, meaning that you will not be favoring one group over the other. Imagine you now going into a military camp and you want to do a research. And that research, you want to see how your outcome influences males and females. And you just go into the military camp and you use simple random sampling to select your sample. Trust me, your simple random sampling will give you a result of maybe 20 males against each female, if not more. So in that case, you will see your data will favor the males more than the female. So in that case, they say you have to do stratified, put the males, all the male military in one side, put all the female military in one side, and use simple random sampling, pick the number you need from male, pick the number you need from female. So if you follow all these probability sampling method, you may likely get an adequate normally distributed data. But in a case where you don't follow this method, you may favor one group over the other. So favoring one group over the other, that data may appear skewed. And if that data is skewed, you're not allowed to use mean because it will give wrong value. So they said, okay, if your data is skewed, please use non-parametric, meaning focus on the median. But if your data is normally distributed, focus on the mean. But sometimes it's not easy to determine whether your data is skewed or not just because of the way you sampled the data. So they have provided some tests, statistical tests to show, which is the Shapiro-Wilk normality test. So you can use that and determine if that data is normally distributed. So you run that test like I showed you. If your p-value is significant, it means your data significantly deviates from normality. Then it means you have to move to non-parametric. So that is how it works. Yeah.
Thank you so much.
Yeah, thank you. Thank you. Ofoma, we still have 3 more after this before we wrap up. Thank you for your patience, for those that have waited. Yeah.
Okay, thank you so much, Doc.
Yeah, thank you.
It's quite impressive. Your choice of words in explaining these statistics has made it so simple for
Thank
most
you.
of us who had a little fundamental of it. Actually, your response to Mrs. Catherine actually got my question to a point, but I
Okay.
want to go on that error. Actually, type
Okay.
1 an error and type 2 is an error. So I want
Yes.
to know on a practical ground, which one is more grievous in terms of committing type 1 error or type 2 error along research?
Well, I would not say which one is more grievous. It depends on the research that you are doing. In the case of, look at the case of the drug one, which is the type 2 now. I mean,
Yeah.
a drug, has a significant side effect, which is supposed to be published so that people can be aware, or the drug company need to go back and say, okay, this drug we have manufactured, though, the side effects are not much. They are even significant, meaning that it may harm the patients. Why not we go back on the drawing board, review the ingredients, the active ingredients and the rest, and come up with something that is better. But the drug company feels like, no, they don't have time. They don't want to spend that money. So they made the researcher change the values so that it will look as if the drug does not have a side effect. That is grievous. It's a type 2 error. It is grievous. Now, look at the other one, which is the type 1 error, where you are, maybe you want to show whether a particular people should do something. Let me just use in a regular case. Somebody driving to work. Now, driving to work, you have road 1 and you have road 2 that you take to drive to work. And you are now doing a research between using road 1 and using road 2. Which one will save your fuel more? And you now did the research, and your research showed that whether you take road 1 or whether you take road 2 or either of them are the same, no significant difference. Both of them use equal consumption of fuel. But you don't like that because you feel that road 1 is closer to your house. And you don't want, and you don't want people taking there. They are really disturbing you. You now tweak the data to now favor road 2 and say, if you take road 1, you will significantly use more fuel. Everybody will now run to road 2 and you're happy. So it depends on the research. It depends on what you are using it to communicate. That's what will now determine whether it's grievous or not actually whether it's type 1 or type 2.
Okay. Oh, thank you so much. Thank you so much.
Thank you too. Yeah. Fino.
Hello.
Yes, sir. Good afternoon.
Yes, afternoon.
Hold on, sir. Thank you so much for the webinar. It was enlightening.
Thank you.
Please, I just have a little question. Is data cleaning ethical?
Yes, data cleaning is very ethical now. It's like telling me you went to buy meat in the market. You went to buy meat. Oh, there. Sorry, just a second. Okay. Yeah. So data cleaning is ethical because it helps you remove noise from the data. It's just like somebody going to the market to buy vegetables and the rest of them, and you're asking me if washing them is good because they had told you that, if you wash the vegetables, you will remove a lot of the greens. So the nutrient will not be there anymore. So just put them in the pot and cook them. No, now. You have to still wash them because the dangers of not washing the vegetables is even more than the benefit of the greens that you're going to get from the vegetables. So the point I'm making is if you don't clean your data, your analysis will not come out well. Yeah.
Okay.
So yes, your analysis will not come out well.
I don't know if data cleaning is the correct term because I was running an analysis. It was animal study. But then we're having should I use the word outliers? There were some that were giving too much of a difference.
Yes, outliers, yes.
Yes, sir. So I was advised to remove those animals or remove those values. I don't know if I'm supposed to do that to make sure that maybe the report goes a certain way, or maybe the error bars will not be as long as they are if I remove the outliers. So that was what I actually wanted to ask if it's ethical.
Yeah, it is. Yes, it is. It is actually ethical to remove outliers, numbers that are out of the ordinary. For example, imagine that you told me that you are collecting data from undergraduate students. And you now do a mean age, and your mean age was 51. Can you imagine that? So having a mean age of 51, you are simply telling me that most of the undergraduate students in that school are above 50 years.
Okay.
So it simply means that there were outliers, meaning there were people that were not students that probably found their way into that data. Especially sometimes you're doing a questionnaire in an environment and the security man may tell you, I'm a student, to interview me, give me, interview me too, because he thinks there are benefits in filling that questionnaire. And as he's filling, he's calling his friend, come and fill this questionnaire. His friend will fill, the other friend will fill. Before you know what is happening, you have noise in your data. So when you now run the mean and now see that the mean is far above what should be in that environment where you collected that data, of course, you have to review that data and clean them up and remove them, because it's going to bias your result. It's going to make your result look like what it's not. So it's ethical, yes. It's ethical to remove outliers, yes.
Thank you so much, sir. Thank you.
Thank you. Thank you too. Yeah. Ike.
Yeah, Dr. Felix, thank you
Yeah.
very much for your delivery. I think that is very wonderful.
Thank
I think
you.
that my question, I sent it through the chat, but I didn't quite get the answer very well.
Okay.
So I just wanted to ask. My
Sure.
question is, from your chart that you gave, when you have a data and then you do the normality, and you
Yes.
find out that it is not normal, you are supposed to use the non-parametric. Is that right? So
Yes. Yes.
when you do that and you get some significant variables, are you supposed to move on to testing, doing a post-doc analysis on them?
Yeah. So that part now I'm not clear, but I can find out and get back to you. So send me a WhatsApp.
Okay.
234806499. So that is my WhatsApp number, because
Okay.
I know we often do post hoc for significant ANOVA.
Yes.
But
Yes.
honestly, I have not done post hoc for significant Kruskawalis.
Yes. Yeah. Yeah.
I
Yeah.
have not had need to. So, most of these things is, them on the need to use basis.
Yes.
Sometimes if you have not done it, you won't bother checking whether it's there or not.
Yeah. Yeah. It's
So,
true. It's true.
yeah, so I've never done it. I've never had need to do a post hoc Kruskawali. So I don't know if it's there, but it's a good thing to actually find. So please do me a WhatsApp message after the webinar. Let me check quickly and come back to you.
All right. Thank you very
Please.
much.
Yeah, thank you too.
Yeah.
Yeah. Yeah. Professor Ngozi.
Hello.
Yeah.
Yes.
Yeah. Professor
Thank you
Ngozi.
very much.
Yes. Yes. Thank
Yes.
you. Thank you, ma'am.
Please. Thank you. My question is, I have come across published research papers where ordinal data are being modified to become discrete data.
Yeah.
In some publications, somebody can use levels, high extent, low extent, or strongly agree, disagree, and then the person will give them numbers. Strongly agree 4, disagree, agree 3, disagree 2, and the other one 1. And then at the end, based on these numbers, there will be a multiplication of the frequencies. And then at the end, the person will use mean and standard deviation to do the analysis. So, but from what I have seen, it is wrong. I'm wondering, is there anything you have to tell me about this?
Okay. All right. So what I have to tell you is, when it comes to data and analysis, most of these principles are not cast in stones. It depends on what you as the researcher wants to achieve, and based on what you want to achieve, you still have to follow standard operating procedures. So the first thing I would say, ordinal variables. If you have ordinal variables or ordinal data that are not numbers on their own, like the example you gave, strongly agree, strongly disagree, and the rest of them. Now, the first thing you do is you represent them in frequency and percentages. So first of all, it tells you the number that says strongly agree, the number that says not strongly, and the rest of them. The second thing you can do, you can transform those into numbers like 1, 2, 3, 4, 5, depending on what you want to achieve. So your strongly agree can be your 5, and your strongly disagree can be your 1. All right. So now it is ordinal numbers. So you can actually use it as an ordinal number and there's room for doing ordinal association. There's one they call Spearman's, Spearman. So meaning that you can use Spearman's to tell that, that there is an odds of movement, or there's an odds of increase from strongly disagree to strongly agree. So meaning that most of the people have odds for strongly agree, because the number that will generate will be closer to the 5, much more than closer to 1. If you want to use the summary statistics, you use the median, because these are discrete numbers. So we would not be able to use mean. So if you use mean, a mean of 1.5, does not really mean anything, because originally they are not numbers. 1 means strongly disagree. I think 3 means undecided. 5 means strongly agree. So if you use a mean of 1.5, so what does that mean? Does that mean in between strongly disagree and disagree? Yeah. So what I can say is, yes, you can use median. Median can give you, after you have gotten your frequency and percentages, you can get a score, meaning you can turn the strongly disagree, all of them, to numbers and get a median value. So if you get a median value of 3, for example, you can still interpret it that most of them, fell into undecided. That's what that means. If you get a median of 4, it means that most of them fell under agree. So yes, you can still convert your ordinal data to numeric values. But in terms of running them statistically, you can use the frequency percentages. But if you want to use the summary statistics, I would recommend median, not mean. Yeah,
Hello?
so I can recommend median and not mean. And yes, it is allowed. So I don't know if there's another aspect that I didn't answer. Sorry.
Thank you so much. I'm grateful.
Yeah, is that all? I don't know. Did I miss anything?
You didn't talk about the Spearmans.
Yeah, so I was saying Spearman is when you are doing ordinal variable, you can use Spearman. Like if you use Pearson's now, Pearson's focus on continuous. Continuous, for example, age and BMI. You can use Spearman's to tell if their age is increasing. Is their BMI significantly increasing? Or if their age is increasing, does that also influence their weight or their height? So when it comes to continuous variable, the flow of the continuous variable, we use Pearson's correlational coefficient. But when it comes to this ordinal, we use Spearman's. It's the same thing. So you can use educational level now, which is increasing from no formal education 1, that will grow to primary 2, secondary 3, tertiary 4, post-tertiary 5. You see, then you can have the Likert scale, strongly agree for COVID-19 vaccine. Sorry, strongly disagree for COVID-19 1, disagree 2, undecided 3, agree 4, strongly agree 5. So you can use Spearman to tell, as the educational level is increasing, as the educational ordinal level is increasing from no formal education to post-tertiary, is their agreement also increasing from strongly disagree, which is 1, to strongly agree, which is 5? Spearman can actually tell you that, but not Pearson's. Pearson's is for continuous, but Spearman's is for ordinal. Yeah.
Thank you so much.
Yeah, thank you. Thank you. Insa, I think after that we have one more and we'll wrap up. Sorry for keeping so many of you still hanging up. Yeah, Insa, please go ahead.
Yeah, hello, Dr. Felix. Thank you so much.
Thank
An
you.
insightful session. Yes. I want to take you back. So
Okay.
I'm watching for oh my goodness. Okay, yes, type 1 and type 2 error right now. So I wanted to ask, is there a way that we could know whether one are committed a type 1 or type 2 error, maybe as a reviewer, not as an analyst now, right? Because as a data analyst, you can commit a type 1 or type 2 error, you know what you have done, and you just spell it out there. Is there a way that, you picking some sort of work, you can know whether one committed a type 1 or type 2?
Well, you can, as a reviewer, you can know if the adjustment is made on the analysis table itself. But you will not be able to know if the adjustment was made. Sorry, let me mute.
Oh, wait.
Okay, yeah, sorry about that. So I was saying is, if the adjustment was done on the table, analysis table itself, you may be able to know. For example, you remember the confidence interval, something I told you. Someone did a confidence interval. The person ran an odds ratio and did a confidence interval. And that confidence interval, there's a 1 in between. But the person now guesstimated a statistical significant difference because the person didn't want to put the exact p-value that is there. The original p-value that is there was like 0.815, which is not significant. The person says, oh, the person reviewing will not know. The person now wrote 0.02. So you reviewing the paper, you can tell that the way this confidence interval is looking, there's no way the p-value will be significant. But if that adjustment is made on the raw data itself, then they now reanalyze and got it right. It may be difficult to tell. But if the adjustment was made on the table after the analysis is done, there's a way you can tell. Another example is, imagine now you are reviewing somebody's work and the person informed you that they actually collected this data from undergraduates, like the example I gave. And when you're reviewing the paper, they are now telling you that the mean age was 16 point something, or the mean age was 15 point something, or the mean age was 40 something, 45 point something. So in that case, you would doubt that average because the population they said they interviewed the data is not the mean that you are seeing. So the point I'm making is, if the adjustment is made on the result itself, sometimes you can pick a few things. Like another example is, the smaller the chi-square value, the more likely the p-value will not be significant. Like, for example, if you have a chi-square value of like 0.355, of course the p-value will not be significant. If you have a chi-square value of 0.00, the p-value will most likely be 1.000. So imagine someone having a chi-square of 0.358 and they now put a p-value of 0.01. Of course, I know p-hacking has happened there. So you can tell by the result, but if that changes is done in the raw data before analysis, it may not be easy to tell.
Thank you so much, sir. That was
All
very
right.
helpful.
Thank you. Yeah. Abdi Karim, I think.
Thank you. Thank you,
Yes.
Professor. You are enriched us for the knowledge and information regarding the to the statistical significance. I have one question for the significance level. Most of us, we said the cutoff of B value and the T value, as well as the confidence interval. Based on that, what's the cut of significance level for the confidence interval, as well as the cut of significance level for the T test? As we know, for B value, it is less than 0.05.
Yeah.
Thank you.
Yeah, exactly. So Abdikarim, I think Abdikarim is based in, I think, Somalia.
Yeah, Somalia.
Yes, yes. And interestingly, yes, I know. Don't worry, I remember.
Yeah,
Don't worry. Yeah. So Abdikarim and myself, we have actually published 2 papers from very high impact journals. I think one was Springer Nature, then the other one was Dove. And he just brought his data to me and said, okay, I have this data, I want to publish it. And both of us worked on it and we're able to get 2 papers in very high impact journal, you know. So it's just to tell you the testament of collaboration. We have never met physically. I know when he came to Abuja in Nigeria, we couldn't meet because I don't know if I was away or so. Yeah. So to answer your question, Abdi Karim, like I mentioned earlier, sorry, let me mute. Somebody is okay. Like I mentioned earlier, confidence intervals, they don't have cutoffs. T-tests, they don't have cutoffs. Chi-squares, they don't have cutoff. The only thing that have cutoff is the p-value. That's why when you run analysis and when these things are generated, they always have p-values at the side. If you run bivariant logistic regression and it generates the odds ratios and the 95% confidence interval, it will always give you p-value at the side. If you run a t-test, it will give you p-value at the side. If you run a chi-square, it will give you p-value at the side. Why is it doing this? Because it knows that just looking at the t-test value or the chi-square value, you may not be able to tell whether there's evidence to reject or accept the null hypothesis. All right. So these things don't have cutoff. So that's why you still have to depend on your p-value. However, I've given you guys a clue how you can use confidence interval to tell whether the association is statistically significant or not. Telling you that if you look at the confidence between the minimum and the maximum value, if there's no one in between that range, then there's a good chance that that P would be statistically significant. But to answer your questions clearly, these things don't have cutoff. So you still have to depend on the p-value cutoff to actually tell if you're going to accept or reject your null hypothesis. Yeah. Thank you. So one final question, if anyone, before we wrap up. Sorry for keeping you guys over time.
Good evening, Doc. Thank you
Yeah,
so
good
much for
evening.
the presentation.
Thank you too.
Sir, I don't want to ask much question. I just want to get your contact. That's your WhatsApp
Okay.
number you called.
Yes, I had put the I can put it again. So I am active on WhatsApp. So if you send me a message on a request, I am happy to do that. So that is my WhatsApp. Yeah. So you can always reach out to me. Yeah. Thank you. Thank you very much. So I think that is it.